In this section, we're going to analyze the dynamics of a coin, and we're going to show that tossing a coin is not really a random process. Let's consider an idealized coin living in two dimensions. The coin has two sides. One side, the red one, corresponds to tails, and the other side, the blue one, corresponds to heads. The coin is tossed at time 0 from the hand that you see right there at the bottom, and it goes up to a certain height and then it falls back down again. Let's analyze the situation using undergraduate dynamics. The first thing I'm going to do is draw the free body diagram of the coin at an arbitrary position, the one you see at the top. I start with the center of mass, which is this point right here in the middle. And then I draw the only force that acts on the particle, which is the force due to gravity, which is of course m times g. I also need some variables to describe the position of the particle. I'm going to use the distance of the particle from the horizontal axis, and I'm also going to use this angle theta, which is the angle that the coin makes with the horizontal axis. Now I'm ready to write down the equations of motion, and these come of course from Newton's laws. So the first one says that the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. And of course here I only have the acceleration of gravity, and the acceleration ay can be written as y double dot. And simplifying, I get this equation, y double dot equals minus g. This is equation number 1. And then I also have Euler's equation, which tells me that the sum of the moments about the center of mass is equal to the moment of inertia times the angular acceleration. Here the sum of moments is 0, and that should be equal to I times theta double dot, which is the angular acceleration. And of course this gives me the equation theta double dot equals 0. It's equation number 2. We've shown that the dynamics of a coin toss can be described with a system of second-order differential equations, which you see right here. And of course, to solve the system of differential equations, you need 4 initial conditions: where the particle is at time 0, what its angle is at time 0, what the initial velocity is at time 0, and what the initial angular velocity is at time 0. Of course, here I have assumed that when I'm tossing the coin, the initial position is 0. This is the position of my hand. And I have also assumed that I'm tossing it from a horizontal position. That's why this angle is 0. And then I only have 2 parameters that control the tossing, and that is, I only have now 2 parameters that control the result of the coin toss: the initial velocity and the initial angular velocity. Given these 2 numbers, I can now predict exactly what the trajectory of the coin is. I actually have the height of the coin as a function of time, and I have the angle that the coin makes with the horizontal axis as a function of time. And you see that these 2 quantities only depend on the initial velocity and the initial angular velocity of the coin. Now I'm letting the coin go, and I'm waiting for it to reach my hand again. This happens when the height becomes 0, and the time at which this happens is given by this expression. It's just 2 times the angular velocity divided by the acceleration of gravity. But it's really the angle with which the coin hits my hand that determines whether I get tails or heads. This angle is given by this expression at the bottom. It's just 2 times the product of the initial velocity and the initial angular velocity divided by the acceleration of gravity. Here in this plot, you see the different possibilities that may arise out of this analysis. On the left, you see angles that result in heads, and on the right, you see angles that result in tails. Alright, so let's now define a variable that corresponds to the result of the coin toss. We're going to call this variable x, and we'll see later on that it is actually a random variable, and this variable takes two values, tails or heads, depending on what the angle of the coin with respect to the horizontal axis does, and it is tails when that angle is between pi over 2 and 3 pi over 2, and that of course is modulo 2 pi, otherwise it is heads. We can also depict the situation using a graphical model representation, and this is what is shown at the bottom. So you see that the random variable x, in order to get its value, it requires a knowledge of the initial velocity and the initial angular velocity, and of course the acceleration of gravity. So this means that if you run the experiment of coin toss in Mars or on the moon, you should expect to get different results because the acceleration of gravity is different. Alright, so we managed to show that the result of a coin toss is just a function of the initial conditions. It is a completely deterministic process. There is nothing random in it. However, if you ask me what is the probability of heads or tails for a particular coin that you hold in your hand, I will still give the answer 50% probability for heads. Where does that come from? This comes from the fact that I do not know the initial conditions, and therefore I cannot predict the result of the coin toss with any accuracy. To understand it, let's look at this graph that shows how the space of initial conditions separates into regions of tails and heads. In particular, the x-axis corresponds to initial velocities and the y-axis corresponds to initial angular velocities. These lines separate the space into regions of heads and tails. Let's zoom in to understand this. If you start here at this point, you're going to get heads. And you're going to get heads pretty much at any point between these two lines. But if you cross the blue line, you're going to get tails. And you're going to get tails at any point between these two lines. And if you cross again, you're going to get heads and tails and heads and tails and so on. So if we operate at this scale of fidelity, if we know the initial conditions with this accuracy, let's say, then we can predict that we're going to get heads or that we're going to get tails. And sometimes when we are at a situation like that, we may get heads or tails with some uncertainty. However, we do not usually operate at this scale. We operate at a scale that looks like this, like the original one we have here. At this scale, this is our state of knowledge about the initial conditions. Any point inside here is fair game. Therefore, we cannot accurately predict whether we're going to get heads or tails. If we wanted to find the probability of heads, the legitimate thing to do is to calculate the relative area of initial conditions that give rise to heads. And it turns out that this relative area is very close to 50%.